So up till now, sine and cosine have only been defined on angles between 0 to 90 degrees. Or you could also do radians, so 0 to pi over 2 radians. And the reason for that is the way we define sine and cosine involves a triangle, in particular a right triangle. So for this right triangle, this angle can only be between 0 to 90 degrees. And that's why sine and cosine are only defined for angles from 0 to 90 degrees. But what would we do if we wanted to define it for higher angles? For example, any real value. Well, the answer to that lies in rethinking the meaning of sine and cosine. So we're going to give a totally different definition of sine and cosine now. That is independent of the original definition. So originally we defined sine to be opposite over hypotenuse. But now we're going to give another way to define it for any angle, except there's one thing we have to make sure, which is that it still coincides with our original definition on angles between 0 to 90 degrees. So as long as these two definitions match up, then we can define our function to be something else on bigger angles. And now it's not immediately clear why you would even want this, but once you see the definition and work with that a little bit more, you'll begin to get an idea for why this might be useful in the future. So now let's start with a right triangle, and we're going to put it on the xy plane. It has hypotenuse 1, and it's got a height and a base, and angle theta, of course. So we've got this point of this triangle, and because it has hypotenuse 1, as long as you just pick a point that's 1 unit away from the origin, drop the perpendicular, you've got yourself a right triangle. So let's compute sine of theta. So sine of theta is equal to opposite over hypotenuse, which is equal to the height over 1, which is just equal to the height. So let's rewrite this for what it actually is. Now let's do cosine of theta. So this is equal to adjacent over the hypotenuse, which is equal to the base over 1. Now base over 1, that's just base. And so the base of our triangle is just cosine of theta. Now that's interesting because that means the coordinates of this point is cosine of theta and sine of theta. So anytime you pick a point that is 1 unit away and you draw your right triangle, the coordinates of this point in terms of the angle of theta that it makes with the x-axis will always be cosine of theta and sine of theta. And that's just according to our definition. So instead of describing this point by its x and y coordinate, I could just tell you that the angle is theta, and then you would know immediately by taking cosine of this angle and sine of theta what the x and y coordinates are. So all I need to do is I need to give you the angle and maybe the distance away from the origin. And then you can compute the actual coordinates. So this gives us a way to extend cosine and sine for bigger angles. Because over here, we picked a point that was 1 unit away and it happened to be in the first quadrant. What if instead we pick a point that's 1 unit away, but in the second quadrant? So let's draw a picture of that. So I'm going to draw a unit circle because if we're picking a point 1 unit away, that's like picking a point on this unit circle that's centered at the origin. So let's say I pick this point. Well, one way that I could describe it is, so I know the the hypotenuse is 1 of this triangle. But one way I could describe it is I could just say, okay, it's 1 unit away from the origin, and the angle that it makes between the x-axis and sort of the line between the point and the origin is theta. Now, what is the x-coordinate and what is the y-coordinate of this point? So we will define them to be cosine of theta and sine of theta. In other words, cosine of theta is the x-coordinate of a point whenever the angle is theta. And sine of theta is defined as the y-coordinate of the point whenever the angle is theta. So when I do this colon equals, that means it's defined as. Angle theta, and remember, of course, we're always picking this on the unit circle, so the distance will always be 1. And sine of theta is the y-coordinate with angle theta and distance 1. So this is how we define it for bigger angles. And the way we picked this definition, it coincides with our original definition for sine and cosine, just because when you do these calculations using the original definition of sine and cosine, you already get that it's the x and y coordinates. So if we just extrapolate and say that it's always the x and y coordinates, then that gives us a definition that extends to bigger angles. Now already you can start to see why this might be useful, because this gives us 2 different ways to describe a point. The typical way that you've been describing points is you give the x-coordinate and you give the y-coordinate. So for example, if I want to tell you how to get to a certain grocery store, I tell you to go 5 units to the right and then go 10 units up. But instead, I could tell you, okay, face in a certain angle and then just go forward. So that would be like me giving you the angle and then the distance. Okay, so in practice, to actually determine these coordinates, you do have to use a little bit of geometry and visualization. So let's look at examples of that. Okay, find cosine of 135 degrees and sine of 135 degrees. Now, I know we had a section on radians, but you might not be 100% comfortable with them just yet. So right now we'll just use degrees. But of course, expect to be able to do the same computations with radians as well. So let's draw this picture first. And let's just say step 1 is always to draw a picture when you're just getting started with this. So step 1, draw a picture. Okay, so what does cosine and sine represent? Well, their new definitions are the x-coordinate and the y-coordinate. So it's the x-coordinate of this point. And sine is the y-coordinate of this point. That's So this is just a geometry problem now. We just need to find the x and the y coordinates of this point using geometry. Okay, so step 2. Relate this to angles that you already know. So in other words, try to find a related triangle that has angles that are between 0 to 90 degrees, is a right triangle, and all of those good things. So we actually already drew that triangle, but we'll draw it clearer now. So if this makes a 135-degree angle, then we can create a triangle by dropping the line from this point, the perpendicular line. And that would give us a 45-degree angle for this triangle. So this is a right triangle with a 45-degree angle. That means it's a 45, 45, 90 triangle. So we know what the lengths of this and this segment are. In fact, so we can write this is going to be cosine of 135 and sine of 135. Now, if this was, let's just compute the absolute length of this. So using our trigonometry, we know that this actual length is going to be cosine of 45, because cosine of 45 degrees, that's going to be adjacent over 1, which is just the length. Let's call it base. But since it's in the negative direction, it's going to be the negative of this. So what that tells us is this x-coordinate, which is cosine of 135, that's going to be equal to the negative of cosine of 45 degrees. And cosine of 45 degrees, we know that's square root of 2 over 2. So that tells us that cosine of 135 is equal to negative square root of 2 over 2. And you can just also do this by looking at the geometry. So if you don't want to use trig, you can just say, okay, what is this length? Well, I know this is a 45, 45, 90 right triangle, and I know it has hypotenuse 1. And I know that the legs are just 1 over square root of 2, because 1 is the hypotenuse. So I could just say that this is negative root 2 over 2. That's the other way to look at it. But it's good to be able to see it in this form. Okay, so now for sine of 135. Well, you can notice that sine of 135, again, it's the height of this triangle. And the other way that we could express the height of this triangle is through this angle as well. So that is going to be sine of 45, because if you think about it, sine of 45, that's equal to height over 1, which is just the height. So we have this equals sine of 45, and that's equal to square root of 2 over 2. And now one thing you notice is that sine of 135, it's the same as sine of 45. And you can see that also from the picture, because if I drew a similar triangle, let's draw it over here, where we have 45 degrees. Well, sine of 45 degrees and sine of 135 degrees, these two triangles will have the same height. So it's not surprising that sine of 135 degrees is equal to sine of 45 degrees, which is square root of 2 over 2. So in general, if you look at the sine and cosine as the angle changes, so if your angle is in this first quadrant, quadrant 1, then sine will be positive and cosine will also be positive. If your angle is in the second quadrant, now cosine becomes negative and sine remains positive. And that's just because your x and y coordinates are negative and positive. Okay, and if you go into the third quadrant, so this is the second quadrant, the third quadrant, well, now you notice that both sine and cosine are going to be negative because both the x and y coordinates are negative. And then finally, if you go into the fourth quadrant, well, now you have cosine is positive, but sine is negative. Okay, so that's it for extending trig functions to bigger angles. Now you might be wondering, okay, how do I define tangent and cotangent and all that? Well, tangent is actually defined through sine and cosine. Tangent, you see, is defined as sine theta over cosine theta. So once you have sine and cosine defined for bigger angles, then you can define tangent of theta for bigger angles. And of course, there's going to be some parts of tangent which are undefined when you're dividing by 0. But in general, you can define it for every other value. Okay, so in the next section, we're going to see how this relates to Pythagorean theorem. So I'll see you there.